Tonight, we're going to go inside the smallest thing physicists have ever found and ask a question that almost no one thinks to ask. Not what the Higgs boson does, and not where it came from, but what it's actually made of. Because here's the thing most people don't realize. The Higgs boson, the particle that supposedly gives everything in the universe its mass, the particle that took 50 years and the largest machine ever built to find, might not be fundamental at all. It might have structure, it might have parts. And if it does, everything we think we know about why matter exists, why you exist, needs to be rebuilt from the ground up. By the end of tonight, you're going to understand not just what the Higgs boson is, but why the question of what it's made of might be the most important question in all of physics. Before we begin, if you enjoy these topics as much as we do, make sure to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. There is a field that fills all of space. Every cubic centimeter of the universe, from the emptiest void between galaxies to the interior of your own body, is threaded through by something invisible. You can't see it. You can't feel it directly. There is no instrument that can point at it and say, "Here it is." But without it, nothing would have mass. Electrons, quarks, the building blocks of every atom, in every star, in every galaxy, would be completely massless. They would race through the universe at the speed of light, never slowing, never binding together, never forming the structures we call matter. There would be no atoms, no molecules, no chemistry, no planets, no you. This field is called the Higgs field, and it is, in a very real sense, the reason anything exists the way it exists. The Higgs boson is what physicists call an excitation of that field. When you pour enough energy into the Higgs field in a small enough region of space, you disturb it, and that disturbance takes the form of a particle, a ripple in something that is otherwise perfectly still. That particle is the Higgs boson, and on the 4th of July, 2012, after searching for it for nearly 50 years, physicists found it. The announcement came from CERN, the European Organization for Nuclear Research, on the Swiss-French border outside Geneva. Both major detector collaborations at the Large Hadron Collider, ATLAS and CMS, announced a discovery simultaneously. It was one of the most significant moments in the history of science. The crowd in the auditorium included Peter Higgs himself, the British physicist who had first proposed the mechanism in 1964. He was 83 years old. When the result was announced, he was seen wiping tears from his eyes. He had spent nearly half a century waiting for this confirmation. But here is where the story gets complicated. The discovery of the Higgs boson was not the end of something. It was the beginning of an entirely different set of questions. Because the moment physicists actually had a Higgs boson to study, they began measuring it. Its mass, its spin, the ways it decays into other particles, the rates at which those decays happen. And some of those measurements came back almost exactly right, almost exactly as predicted. Almost, but not quite. And in physics, almost is a very interesting word. The standard model of particle physics is the most successful scientific theory ever written down. It describes, with extraordinary precision, the behavior of all known fundamental particles and the forces that govern them, with one major exception we'll come back to. It predicted the existence of particles decades before experiments could find them. It made numerical predictions accurate to more than 10 decimal places. When the theory says an electron's magnetic moment should be 2.00231930,436, and you measure it and get exactly that, you start to trust the theory. The Standard Model is built on a framework called quantum field theory. The basic idea is that space is not empty. It is filled with fields. Every type of particle corresponds to a field that permeates all of space. An electron is an excitation of the electron field. A photon is an excitation of the electromagnetic field. A quark is an excitation of a quark field. And the Higgs boson is an excitation of the Higgs field. These fields interact with each other according to rules that can be written down as precise mathematical equations. The interactions produce what we observe as forces: electromagnetism, the weak nuclear force, the strong nuclear force. The Standard Model describes all of these beautifully. It does not describe gravity. That is the exception. General relativity handles gravity, and the two frameworks, quantum field theory and general relativity, have so far refused to be unified into a single, consistent description. That problem is real, enormous, and separate from what we are discussing here. But within its domain, the Standard Model is a machine that simply works. The Higgs field occupies a unique position within it. The other fields in the Standard Model acquire their properties from the mathematics of the theory. The photon is massless because of a symmetry in the equations. The gluon is massless for a related reason, but the Higgs field is different. The Higgs field has what's called a non-zero vacuum expectation value. That is a technical phrase with a very specific meaning. It means that even in its lowest energy state, even when the universe is as calm and empty as it can be, the Higgs field does not sit at zero. It sits at a specific non-zero value, like a ball at the top of a perfectly symmetric hill that has rolled off to one side and settled there. The exact value it settles at is 246 giga-electron-volts. And that non-zero value is what breaks the symmetry of the Standard Model. It is what allows particles to have mass. This mechanism is called electroweak symmetry breaking. It is one of the most elegant pieces of physics ever discovered. To understand what the Higgs field actually does, you need to understand what mass means at a fundamental level. Because mass is not what most people think it is. When you pick up a rock and feel its weight, you are feeling two things: gravity pulling on the rock and the rock's resistance to being moved, what physicists call inertia. Both of these are related to mass, but neither one is mass itself. Mass, at its deepest level, is a measure of how strongly a particle interacts with the Higgs field. Particles that interact strongly with the Higgs field have high mass. Particles that interact weakly have low mass. And particles, like the photon, that don't interact with the Higgs field at all are completely massless. The technical term for this interaction is a Yukawa coupling. Each type of fundamental particle has its own coupling strength to the Higgs field. The top quark, the heaviest known fundamental particle, has a Yukawa coupling close to 1. That means it interacts with the Higgs field about as strongly as it possibly can. The electron has a coupling of about 3 × 10⁻⁻⁶. It interacts with the Higgs field only faintly. That is why the top quark is about 339,000 times more massive than the electron. Not because they are made of different stuff in any obvious sense, but because they couple to the Higgs field in very different ways. These coupling values are put into the Standard Model by hand. The theory does not predict them. It accommodates them. You measure the mass of each particle, you calculate its coupling constant, and you write it in. Physicists call numbers like these free parameters. There are about 20 such parameters in the Standard Model. They are measured, not derived. And that bothers physicists deeply. Because a truly fundamental theory should explain why those numbers are what they are, not just accept them as inputs. A theory that simply accommodates every measurement without explaining any of them is, in a sense, not a theory at all. It is a catalogue. The Standard Model, as magnificent as it is partly a catalogue, and the Higgs sector is where that limitation is most visible. The coupling of the electron to the Higgs field is about 340,000 times smaller than the coupling of the top quark to the Higgs field. No one knows why. It is what it is. Written in. Accepted, not explained. That gap in understanding is where new physics must eventually live. Now, we arrive at the real question. What is the Higgs boson made of? In the Standard Model, the honest answer is nothing. It is a fundamental particle, point-like, structureless, with no internal components. Like an electron or a quark, it is one of the basic ingredients of reality, not assembled from anything smaller. But here's why that answer is deeply unsatisfying. The Higgs boson has a mass of approximately 125.25 giga-electronvolts. A giga-electronvolt, or GeV, is a unit of energy used in particle physics, where energy and mass are interchangeable through E equals mc squared. 125 GeV means the Higgs boson is about 133 times heavier than a proton. For reference, a proton has a mass of about 0.938 GeV. So, the Higgs is heavy. Not the heaviest particle, the top quark at about 173 GeV takes that prize, but solidly in the high end of the mass spectrum. And that mass creates a problem. A deep, uncomfortable problem called the hierarchy problem. Here is how it works. In quantum field theory, every particle interacts with every other particle through quantum fluctuations. Virtual particles pop in and out of existence everywhere in space, even in total vacuum. These fluctuations are not hypothetical. They produce measurable effects on real particles. The Casimir effect, where two uncharged metal plates placed very close together are pushed toward each other by vacuum fluctuations of the electromagnetic field, is one of the cleanest demonstrations that quantum fluctuations are physically real. They measured it in the lab. The force is there. The vacuum is not empty. It is seething with quantum activity. These fluctuations contribute to the physical properties of particles, including their mass. The technical term is radiative corrections. When you calculate the Higgs mass by summing up all the contributions from all these quantum fluctuations, you get a number that is almost infinitely large, far larger than what we measure. Specifically, the corrections push the Higgs mass toward the highest energy scale in the problem. In particle physics, the most natural high energy scale is the Planck scale, the energy at which quantum gravitational effects become important. The Planck scale is about 10 to the power of 19 GeV, 1 followed by 19 zeros, in units of giga-electronvolts. The Higgs mass is about 125 GeV. The ratio of the observed Higgs mass to the Planck scale is roughly 10 to the power of -17. To get a sensible answer out of the calculation, something has to cancel those corrections almost perfectly. The technical word for this precise cancellation is fine-tuning. The degree of fine-tuning required to get the Higgs mass right is approximately 1 part in 10 to the power of 34. 10 to the power of 34. 1 followed by 34 zeros. Physicists call this the hierarchy problem, and it is one of the most uncomfortable facts in modern physics. Because fine-tuning at that level does not happen by accident in nature. When you see a balance that precise, your first instinct is that something is keeping it in place. There is a mechanism. There is a reason. The question is what? And the answer to that question almost certainly involves the Higgs boson being something more than a structureless point. Before we go into what that something more might be, it helps to understand the historical precedent. Because the hierarchy problem is not the first time physicists have encountered an uncomfortable sensitivity of this kind, and the solution has never been fine-tuning. It has always been new structure. In the 1960s, the proton was considered fundamental. It was on the list of basic building blocks of matter, along with the electron, the neutron, and a growing zoo of other particles being discovered in accelerators around the world. The proton was where physics stopped. Below the proton, nothing. Then, experiments at the Stanford Linear Accelerator Center in California in 1967 and 1968 began revealing something unexpected. Physicists fired high-energy electrons at protons and watched how the electrons scattered. At low energies, the electrons scattered off the whole proton as if hitting a small, featureless ball. But at higher energies, the scattering pattern changed fundamentally. The electrons were bouncing off of individual point-like objects inside the proton. Not the proton as a whole, something smaller. Those objects are what we now call quarks. The proton is not fundamental. It is made of 3 quarks, bound together by a new force, the strong nuclear force, mediated by particles called gluons. This was one of the defining discoveries of 20th century physics. James Bjorken worked out the theoretical framework for understanding the scattering at high energies. Richard Feynman contributed the Parton model interpretation. Murray Gell-Mann and George Zweig had independently proposed quarks as mathematical objects in 1964, before any direct evidence for them existed. The deep inelastic scattering experiments at Stanford confirmed that the quarks were real, physical objects inside the proton. The proton dissolved, conceptually, into something smaller and more fundamental. This pattern of looking inside something we thought was fundamental and finding structure has repeated itself throughout the history of physics. Atoms into nuclei and electrons. Nuclei into protons and neutrons. Protons and neutrons into quarks. The Higgs boson is the next candidate. And the hierarchy problem is the theoretical hint that the pattern might be about to repeat. Something is wrong with the Higgs at the level of the Standard Model alone. Something needs to fix it. And the most historically consistent fix is new structure. There are several serious proposals for what might resolve the hierarchy problem. The first and most famous is supersymmetry. Supersymmetry is a proposed symmetry between 2 fundamentally different types of particles. In the Standard Model, particles come in 2 varieties: fermions, particles with half-integer spin like quarks and electrons, the matter particles, and bosons, particles with integer spin like photons and gluons, the force-carrying particles. The Higgs boson is also a boson, with spin 0. Supersymmetry proposes that every fermion has a bosonic superpartner, and every boson has a fermionic superpartner. The electron has a superpartner called the selectron. The quarks have superpartners called squarks. The gluon has a superpartner called the gluino. The Higgs boson has fermionic superpartners called Higgsinos. These superpartners have not been observed. If they existed at low energies, we would have found them by now. But they might exist at higher energies than current colliders can reach. The reason supersymmetry was originally exciting, beyond being mathematically elegant, is that in a supersymmetric theory, the quantum corrections to the Higgs mass cancel exactly. Every contribution from a standard model particle to the Higgs mass is precisely cancelled by the contribution from its superpartner. Fermion loops and boson loops contribute with opposite signs. In a supersymmetric theory, those opposite sign contributions cancel perfectly. The hierarchy problem disappears. Not by accident, but by symmetry. A beautiful resolution. But supersymmetry does not resolve the question of what the Higgs is made of. In supersymmetry, the Higgs boson is still fundamental, still structureless, still point-like, still an elementary degree of freedom. Supersymmetry solves the hierarchy problem without answering the compositeness question, which is why it has always coexisted with other proposals that take a more radical step. That more radical step is the idea that the Higgs boson is not fundamental at all, that it is a composite particle, assembled from smaller, more fundamental constituents, held together by a new force. This idea has a name, compositeness, and it has the historical precedent we just discussed. If the Higgs is composite, if it is assembled from smaller constituents, then its mass is set naturally by the energy scale of whatever new force binds those constituents together. No fine-tuning required. The mass of a proton is not fine-tuned. It emerges naturally from the dynamics of the strong force that binds its quarks. The proton mass of about 0.938 GeV is set by the energy scale at which the strong force becomes strong enough to confine quarks into bound states. That energy scale is called the QCD confinement scale, around 200 MeV. The proton mass is of the same order. A composite Higgs could work the same way. If there is a new force, something analogous to QCD, but operating at a higher energy scale, and if that force confines new fundamental particles into a bound state, the mass of that bound state would be naturally of order of the confinement scale. You would not need fine-tuning to explain why the Higgs mass is much smaller than the Planck scale. The Higgs mass would be determined by the confinement scale of the new force. And if that confinement scale is a few TeV, a few tera-electron volts, the Higgs mass would naturally come out around the electroweak scale, around 100 GeV, close to what we observe. The hierarchy problem is not solved by cancellation, as in supersymmetry. It is solved by natural dynamics, by the same mechanism that gives the proton its mass. No tuning, no special choice of parameters, just the physics of confinement. The most developed composite Higgs framework historically is called Technicolor. Proposed in the late 1970s by Leonard Susskind at Stanford and independently by Steven Weinberg at Harvard, Technicolor was a bold reimagining of electroweak symmetry breaking. Instead of a fundamental scalar Higgs field, you have a new force, the Technicolor force, and new fundamental particles called technifermions. The Technicolor force is a scaled-up version of QCD. Just as QCD confines quarks into protons and pions, the Technicolor force confines technifermions into bound states at a higher energy scale. And just as the pion of QCD is a pseudo-Nambu-Goldstone boson, a particle whose existence is tied to a broken, approximate symmetry, the would-be Higgs boson in Technicolor is a bound state of technifermion pairs. Electroweak symmetry would be broken by the condensation of technifermion pairs in the vacuum, similar to how superconductors form Cooper pairs of electrons. No fundamental scalar field needed. No fundamental Higgs boson. Just bound states of technifermions produced by a new force. It was a beautiful idea. Elegant in exactly the way physicists hope their theories will be. And it mostly does not work. Original Technicolor models ran into severe problems with precision measurements of electroweak observables. The W and Z bosons had been discovered at CERN in 1983 by Carlo Rubbia and Simon van der Meer's team, confirming a key prediction of the electroweak theory. After the discovery, precision measurements of the W and Z masses and their interaction rates became powerful probes of new physics. The S parameter and T parameter are two combinations of measured electroweak quantities that constrain how strongly any new physics can affect the electroweak sector. Early Technicolor models predicted values for these parameters that conflicted with measurements from the Large Electron-Positron Collider at CERN in the 1990s. The simplest versions were ruled out. What followed was a period of intense theoretical work trying to save the basic idea by making it more sophisticated. Walking Technicolor proposed a Technicolor force with different behavior at different energy scales, chosen to reduce the problematic corrections. Top-color models added a new strong force specifically for the top quark, addressing its unusually large mass separately. Top Technicolor combined these ideas into unified frameworks. Each variation addressed specific problems and introduced new ones. The theoretical landscape became complicated. Some versions remained viable, but then the Higgs boson was discovered in 2012 with a mass of about 125 GeV, and that complicated things further. Because a fully composite Higgs made entirely of technifermions would generally produce couplings to other particles that deviate significantly from standard model predictions. The deviations would be of order 1, meaning roughly 100% difference in some coupling. That is not what was measured. The measured couplings are close to standard model values. So, if the Higgs is composite, it is a very particular kind of composite, one that mimics an elementary particle extremely well, one that requires a more subtle theoretical framework than simple Technicolor. This is where the most interesting, modern frameworks come in. Composite Higgs models with a pseudo-Nambu-Goldstone boson structure. The key concept is a pseudo-Nambu-Goldstone boson. To understand what that is, you need to understand Emmy Noether. Emmy Noether was a German mathematician working in the early 20th century. In 1915, she proved a theorem that turned out to be one of the cornerstones of modern physics. Noether's theorem states that every continuous symmetry of a physical system corresponds to a conserved quantity. If a system is symmetric under rotation in space, angular momentum is conserved. If it is symmetric under translation in time, meaning the laws of physics are the same yesterday as today, energy is conserved. If it is symmetric under translation in space, momentum is conserved. These are not coincidences. They are deep mathematical connections between symmetry and conservation. The reverse also has profound implications. When a continuous symmetry is spontaneously broken, meaning the equations respect the symmetry, but the actual ground state of the system does not, something remarkable happens. Massless particles appear. These are called Nambu-Goldstone bosons. Named after Yoichiro Nambu, who received the Nobel Prize in Physics in 2008 for related ideas, and Jeffrey Goldstone, who formalized the theorem in 1961. The pions, the particles that mediate interactions between protons and neutrons in the nucleus, are the best-known example in particle physics. The equations describing the strong force have an approximate symmetry called chiral symmetry. When the strong force confines quarks into hadrons at low energies, that chiral symmetry is spontaneously broken. The pions are the Nambu-Goldstone bosons of that breaking. Because the symmetry is only approximate, not exact, the pions are not exactly massless. They are light compared to the proton and other hadrons, but they are not zero. They are pseudo-Nambu-Goldstone bosons. Pseudo, because the symmetry that produced them is only approximate. The composite Higgs models propose something similar for the Higgs itself. There is a new strong force at a higher energy scale. This force is governed by a symmetry group. When the interaction confines new constituents at some energy scale, it spontaneously breaks a larger symmetry group down to a smaller subgroup. The Higgs boson emerges as a pseudo-Nambu-Goldstone boson of that broken symmetry. Because it is a pseudo-Nambu-Goldstone boson, its mass is protected by the approximate symmetry. Quantum corrections to its mass are suppressed. No fine-tuning. And because the symmetry is only approximate, the Higgs mass is non-zero, but naturally much smaller than the compositeness scale. The ratio of the Higgs mass to the compositeness scale is calculable from the dynamics. No arbitrary numbers inserted by hand. This is why these models are taken seriously. They offer a genuine mechanism for why the Higgs mass is what it is. Not an accident. Not fine-tuning. A consequence of structure. The simplest composite Higgs model is built on the coset space, SO5 over SO4. SO5 is the special orthogonal group in 5 dimensions, a mathematical object describing rotations in 5-dimensional space. SO4 is the same object for 4 dimensions. The notation SO5 over SO4 describes the mathematical space that remains when the larger symmetry group is broken to its subgroup. The mathematics of this symmetry breaking produces exactly 4 Nambu-Goldstone bosons. 3 of them get absorbed by the weak forces W and Z bosons, giving those particles their mass. This is the same mechanism as in the Standard Model, but now the Higgs is a bound state rather than a fundamental field. The 4th Nambu-Goldstone boson is what we call the Higgs boson. The appeal of this construction is that the ratio of the Higgs vacuum expectation value to the compositeness scale, usually called Xi, controls how much the Higgs deviates from elementary particle behavior. When Xi is small, meaning the Higgs vacuum expectation value is much smaller than the compositeness scale, the Higgs looks almost exactly like an elementary particle. Current measurements from the Large Hadron Collider constrain Xi to be no larger than about 0.1, 10%. The compositeness scale is therefore at least several TeV above the energy of current LHC runs. That is why we haven't seen the constituents yet. They are hiding just above where we can look. Like the quarks inside the proton, before the Stanford accelerator could reach the energy needed to see them scatter individually. Now, the question of what those constituents actually are. In analogy with the proton, they would be something like quarks for the Higgs field. Physicists call them by various names depending on the model. Preons is a generic term for hypothetical subcomponents of quarks and leptons. In composite Higgs contexts, the bound states are sometimes called hyperquarks, or technefermions if the binding force resembles QCD. What these constituents have in common across most models is that they carry charges under a new force. This new force acts similarly to the strong nuclear force, but at a higher energy scale. The strong nuclear force is described by QCD, quantum chromodynamics. Its coupling strength is large at low energies, which is why quarks are confined inside protons and can't escape individually. At high energies, the coupling becomes smaller. Individual quarks behave almost freely inside a very fast collision. This property is called asymptotic freedom, and it was discovered in 1973 by David Gross, Frank Wilczek, and David Politzer, who received the Nobel Prize in Physics for it in 2004. The hypothetical force binding Higgs constituents would have the same qualitative behavior. At energies above the compositeness scale, you would see the constituents moving freely. At lower energies, they would be confined into bound states, like the Higgs boson. The nature of those bound states would determine the entire spectrum of particles the model predicts. Not just the Higgs boson, but a whole family of heavier particles, analogous to the heavier mesons and baryons above the pion in the QCD spectrum. The rho mesons, the omega mesons, the eta prime, all part of the bound state spectrum of the strong force. The composite Higgs would come with an analogous spectrum. Heavier vector resonances at the TeV scale, fermionic partners of the Higgs constituents, new scalar particles beyond just the one we found. These are the signatures that particle physicists search for at the Large Hadron Collider, and so far they have not been found. But the search is ongoing, and the limits being placed on these particles are pushing the models into more constrained parameter regions, which is progress. Even the absence of a signal is information. The Large Hadron Collider has collected an enormous amount of data. Its two main experiments, ATLAS and CMS, each hold datasets from Run 1, Run 2, and Run 3. The LHC ran at a center of mass energy of 13 TeV in Run 2 and 13.6 TeV in Run 3. The analyses of the Higgs couplings from those datasets are remarkably precise. The coupling of the Higgs to bottom quarks, to tau leptons, to W bosons, to Z bosons, to top quarks, to photons, all have been measured, and all of them agree with standard model predictions to within a few percent, some even to within 1 or 2%. This tight agreement is both reassuring and frustrating. Reassuring because the theory works. Frustrating because there is no sign yet of what lies beneath. If the Higgs is composite at the few TeV scale, there should be deviations. Small ones, of order psi, but detectable. Some analyses see small hints, a 2% excess here, a 1% deficit there. But none of these are significant enough to claim as new physics. They could easily be statistical fluctuations. They could be systematic effects not perfectly accounted for. Physicists are careful about this. You do not claim a discovery until the evidence reaches 5 sigma, meaning the probability of a statistical fluctuation producing that signal is less than 1 in 3.5 million. Current hints in Higgs coupling measurements are nowhere near 5 sigma, so the status right now is the Higgs looks elementary, but the precision of our measurements is not yet sharp enough to rule out a composite nature at the level predicted by the best composite Higgs models. The high luminosity LHC upgrade is expected to change this. The HL-LHC, scheduled to begin operations in the early 2030s, will collect about 10 times more data than all previous LHC runs combined. That data will allow Higgs coupling measurements with per-mil precision, meaning a few tenths of a percent. If the Higgs is composite with Xi at the level of 5% or larger, the HL-LHC should see it. If it does not, that pushes the compositeness scale to higher energies and Xi to smaller values. It makes composite models more constrained, but does not rule them out. There are also proposals for future colliders that would go further. The Future Circular Collider, or FCC, would have a circumference of about 91 kilometers, almost 3.5 times the size of the LHC, which sits in a tunnel 27 kilometers in circumference beneath the Swiss-French border. The FCC, in its first phase as an electron-positron collider, called FCCE, would produce millions of Higgs bosons in very clean conditions. Electron-positron collisions are cleaner than proton-proton collisions because electrons and positrons are fundamental particles. When they collide, you know exactly what went into the collision. With proton-proton collisions, you are really colliding quarks and gluons, and you have to account for the internal structure of the proton. That introduces uncertainties that limit precision. FCCE would improve precision on Higgs couplings by another factor of 5 to 10 beyond the HL-LHC. The second phase of the FCC, as a proton-proton collider at 100 TeV, called FCCHH, would then push into entirely new energy territory. The Circular Electron-Positron Collider proposed in China, the CEPC, would do similar things to FCCE. All of these proposals are motivated substantially by the need to understand the Higgs boson at a deeper level. The stakes are high enough that multiple countries are willing to spend tens of billions on the infrastructure needed to study this one particle more carefully. That tells you something about how important the question is. There is another angle to the compositeness question that goes beyond just measuring Higgs couplings. If the Higgs is composite, then at some high energy, you can resolve its internal structure. You can see the constituents. You can scatter off of them individually. This is exactly what the deep inelastic scattering experiments did for the proton in the 1960s. Fire a particle at a proton with enough energy, and instead of it bouncing off the whole proton, it bounces off an individual quark inside. The pattern of the scattering tells you how many quarks there are, what their charges are, how fast they are moving around inside the proton. The same principle applies to a composite Higgs. At energies above the compositeness scale, you would no longer produce a single Higgs boson in the usual way. You would instead produce pairs or groups of the fundamental constituents directly. Their interactions would be described not by the Higgs field equations, but by the new strong force that binds them. And the scattering patterns in colliders would change completely. A future collider at 100 TeV of center of mass energy could potentially reach compositeness scales of tens of TeV. If the Higgs is composite at that scale, the FCC-H might not just measure deviations in Higgs couplings. It might directly produce the constituents. see the Higgs dissolve into its components at high energy. Just as the proton dissolves into quarks and gluons when you hit it hard enough. That would be the definitive answer. Not a deviation, not a hint, but direct observation of the structure inside the Higgs, the particle physics equivalent of watching the proton come apart for the first time. There is another class of ideas that deserves careful attention: extra dimensions. In the late 1990s, several groups of physicists realized that if there are additional spatial dimensions beyond the three we experience, some of the most puzzling features of particle physics could be explained geometrically. The most developed framework of this kind comes from Lisa Randall and Raman Sundram. Their 1999 papers proposed that the universe has a fifth dimension that is curved in a specific way. The geometry is called anti-de Sitter space. It is a five-dimensional space with a negative cosmological constant. In this picture, there are two four-dimensional surfaces called branes, separated along the fifth dimension. Gravity is concentrated near one brane, called the Planck brane. The standard model fields, including the Higgs, lie on the other brane, called the TeV brane. The gravitational field spreads through the fifth dimension, but its amplitude decays exponentially as you move away from the Planck brane toward the TeV brane. By the time you reach the TeV brane, the effective Planck scale, the energy at which gravity becomes strong, has been exponentially suppressed. A modest extra dimension can produce an exponential hierarchy. The Planck scale of 10 to the power of 19 GeV gets mapped to a TeV scale by this exponential warp factor. The hierarchy problem is resolved geometrically. No fine-tuning of parameters. The smallness of the Higgs mass compared to the Planck mass is a consequence of the geometry of the extra dimension. In these models, the Higgs boson can be identified with a component of the gauge field in the extra dimension. A five-dimensional gauge field has 5 components. 4 of them behave like a standard four-dimensional gauge field. The 5th component, pointing along the extra dimension, becomes a four-dimensional scalar field when the extra dimension is compactified. This is called gauge-Higgs unification. The Higgs boson is, in this picture, the 5th component of a 5-dimensional vector boson. In this sense, the Higgs has structure in an extra-dimensional sense. It is composite in the extra dimension, even if it appears elementary in the 4 dimensions we directly probe. The masses of the Kaluza-Klein excitations, heavier copies of standard model particles that arise from the extra-dimensional nature of the fields, would appear at the TeV scale. ATLAS and CMS have searched extensively for Kaluza-Klein gravitons and Kaluza-Klein gauge bosons. Mass limits of several TeV have been placed on the lightest resonances. The simplest Randall-Sundram models are constrained. More complicated versions, with additional ingredients to suppress dangerous processes, remain allowed and actively studied. The connection between extra dimensions and composite models is not just analogical. In 1997, Juan Maldacena proposed something extraordinary, a mathematical duality between two completely different types of theories. On one side, a quantum field theory in 4 dimensions with no gravity. On the other side, a gravitational theory in 5 dimensions with a negative cosmological constant, anti-de Sitter space. The claim is that these two theories describe the same physics. They are dual to each other. A calculation in the 4-dimensional field theory corresponds to a calculation in the 5-dimensional gravitational theory. This duality is called the anti-de Sitter, conformal field theory correspondence, or ADS, CFT. It has been one of the most fertile ideas in theoretical physics for the last 3 decades. What does this have to do with the Higgs boson? Randall-Sundrum extra-dimensional models are, through this correspondence, dual to composite field theories. The Kaluza-Klein excitations of the extra-dimensional model correspond to the bound states of the composite theory. The warp factor of the extra dimension corresponds to the running of the coupling in the new strong force. This means that composite Higgs models and extra-dimensional models are not just analogous. They are related by a precise mathematical duality. If you solve the composite model, you get the same answer as solving the extra-dimensional model. They are different descriptions of the same underlying physics. This duality makes composite Higgs models more tractable. Calculations that are difficult in the strongly coupled 4-dimensional theory become calculable in the weakly curved 5-dimensional gravitational theory. And it has deepened the theoretical understanding of what compositeness means. In a sense, asking whether the Higgs is composite is asking whether there is a higher dimensional description of reality, where the extra dimension encodes the internal structure of what we see as an elementary particle in 4 dimensions, a different framing, but the same experimental predictions, the same vector resonances, the same fermionic partners, the same deviations in Higgs couplings. Because the physics is the same, regardless of which description you use to calculate it. There is yet another framework that has received significant attention in the last 2 decades. The twin Higgs mechanism. Proposed around 2005 by Zakaria Chacko, Hokseng Go, and Roni Harnick, it is one of the more creative responses to the hierarchy problem. The basic observation is that the hierarchy problem arises primarily because of one specific quantum correction: the correction from top quark loops. When you calculate quantum corrections to the Higgs mass, the largest contribution comes from diagrams involving the top quark. The top quark is the heaviest standard model particle, with a mass of about 173 GeV, and its large mass means its coupling to the Higgs is close to 1. That large coupling, combined with the fact that the top quark appears in many quantum diagrams, makes its contribution to the Higgs mass the dominant one. In supersymmetry, you cancel it with the stop squark. In composite Higgs models, the structure of the composite state suppresses it. The twin Higgs mechanism does something different. It postulates a mirror sector, a twin of the standard model that is a complete copy of all particles and forces, but which interacts with the visible sector only through the Higgs. The mirror sector has its own twin top quark, its own twin W and Z bosons, its own twin electrons and quarks. None of these particles interact with your detector directly. They are not charged under electromagnetism as we know it. They do not interact via the strong force as we know it. But the twin top quark produces its own quantum correction to the Higgs mass. And the two corrections, from the ordinary top and the twin top, cancel each other. The largest contribution to the hierarchy problem is eliminated. The Higgs mass is naturally stable against corrections from the top quark sector. The twin Higgs model is elegant because it achieves this cancellation not through a new symmetry between bosons and fermions, as in supersymmetry, but through a discrete symmetry that swaps the standard model sector with its twin. The phenomenological signatures are different from standard composite Higgs models. The twin Higgs predicts exotic Higgs decays, where the Higgs sometimes decays into long-lived particles from the twin sector that travel a macroscopic distance inside the detector before producing a signal. These are called long-lived particle signatures, and they require specialized detector strategies. The twin Higgs also predicts missing energy signals because some decay products escape the detector entirely. These signatures are actively being searched for at ATLAS and CMS. So far, nothing definitive. But the searches are far from exhaustive. The parameter space is large, and the detectors are being upgraded. There is something that deserves revisiting here, now with more depth. Because the story of the Higgs giving things mass is not wrong, but it is incomplete in a way that matters. The Higgs mechanism gives mass to elementary particles. Electrons, quarks, W bosons, Z bosons. These particles are massive because they interact with the Higgs field. But the proton, which makes up most of the mass of your body and everything around you, gets only about 1% of its mass from the Higgs mechanism. 1%. The other 99% comes from somewhere else. Specifically, from the kinetic energy and interaction energy of the quarks and gluons inside the proton. The quarks are constantly moving around inside the proton at significant fractions of the speed of light. The gluons carry momentum and energy. They bind the quarks together with enormous force. All of that energy contributes to the proton's mass through E equals mc squared. Mass is equivalent to energy. The proton is heavy not primarily because of the Higgs field, but because of the frantic quantum activity of the strong nuclear force inside it. This is one of the most counterintuitive facts in physics. Most of the mass you feel when you pick up a rock is not coming from the Higgs field. It is coming from quantum chromodynamics, the confinement of quarks. The same general mechanism we said might be producing a composite Higgs. The Higgs mechanism is essential for giving quarks any mass at all. Without it, quarks would be massless, and the dynamics of QCD would produce hadrons with very different masses than we observe. The pion masses, the proton-neutron mass difference, the entire spectrum of hadrons would be altered. The Higgs is a necessary ingredient, but not the dominant one for the mass of ordinary matter. What this means is that the question of what gives things mass does not have a single answer. For elementary particles like electrons, the answer is the Higgs field. For composite particles like protons, the answer is mostly QCD. For atoms, molecules, and everything built from them, the dominant source of mass is the strong force binding the quarks inside nucleons. The Higgs is the foundation. But most of the mass of the visible universe is built on top of that foundation by other forces. The Higgs made the quarks heavy enough to matter, and then the strong force built the rest. The deeper question then becomes, where did the Higgs field itself come from? Why does it exist? What is it, fundamentally? In the Standard Model, the Higgs field is simply postulated. You need electroweak symmetry breaking. You need the W and Z bosons to be massive. You need electrons and quarks to have mass. So you introduce a field that does all those things. You pick the simplest possible field that works. A complex doublet of scalar fields. 4 real components in total. 3 of them get absorbed by the W and Z bosons through the Braut-Inglet Higgs mechanism, giving those vector bosons their mass. 1 remains as a physical particle, the Higgs boson. It is the minimal implementation. elegant in its economy, but not explanatory. It does not tell you why. It tells you what. Every alternative to the elementary Higgs is an attempt to answer the why. Supersymmetry, says the Higgs, is elementary but protected by a symmetry between bosons and fermions. Technicolor says the Higgs is a bound state of a new type of quark. Composite Higgs models say the Higgs is a pseudo-Nambu-Goldstone boson of a broken symmetry. Extra dimensions say the Higgs is a gauge field component in a higher dimensional space. The twin Higgs says the hierarchy problem is solved by a mirror copy of the entire standard model. Each of these is a story about where the Higgs field comes from. Each of them has mathematical substance. Each of them is falsifiable, at least in principle, by experiment. And none of them is confirmed. The uncomfortable situation is that we have multiple viable theoretical frameworks and no experimental evidence distinguishing between them. Every physicist you ask will have a favorite. And they will tell you, with varying degrees of candor, that their favorite is motivated more by theoretical elegance than experimental evidence. Because the evidence is not yet there. Even if we accept that the Higgs is elementary, there is still the question of why the Higgs potential has the shape it has. The Higgs potential is the mathematical function that describes how the energy of the Higgs field varies with its value. In the standard model, the Higgs potential has a specific shape. At the origin, where the field value is 0, there is a local maximum. The origin is an unstable equilibrium, like a ball balanced exactly at the top of a hill. Away from the origin, the potential first decreases and then increases again. It has a minimum at a non-zero field value. Multiple minima, arranged symmetrically around the origin, like the bottom of a wine bottle. When the universe cooled below a critical temperature in the very early moments after the Big Bang, the Higgs field could not stay at 0. The 0 value was unstable. The field rolled toward one of the minima. That is, electroweak symmetry breaking. That is the moment when particles acquired mass. Before that moment, the electroweak symmetry was unbroken. The W, Z, and photon were all massless. Quarks and electrons were massless. Everything traveled at the speed of light. The universe was a plasma of massless particles, interacting at incredible rates, completely uniform in a way that it would never be again. Then, the Higgs field settled into its minimum, and the symmetry broke. The W and Z bosons acquired mass. Quarks and electrons acquired mass. The universe changed its character fundamentally in a fraction of a second. This transition is called the electroweak phase transition. And one of the open questions in physics is exactly what this transition looked like. Was it a sharp, discontinuous jump, a first-order phase transition like water freezing into ice? Or was it a smooth crossover, where the change happened gradually, with no sharp boundary? The standard model predicts that for a Higgs mass of about 125 GeV, the electroweak phase transition is a smooth crossover, not a sharp transition. This has an important implication for one of the great mysteries in cosmology. We live in a universe dominated by matter. But the laws of physics as we know them treat matter and antimatter nearly identically. So, why isn't the universe half matter and half antimatter? Why didn't the matter and antimatter produced after the Big Bang annihilate each other completely, leaving only radiation? The answer must involve some mechanism that created a small excess of matter over antimatter in the very early universe. A first-order electroweak phase transition provides the conditions needed for generating that asymmetry. During a first-order transition, bubbles of the new phase nucleate and expand through the old phase. At the bubble walls, matter and antimatter can be processed asymmetrically if the right conditions are met. A smooth crossover does not provide this, and the standard model predicts a smooth crossover. This is another piece of evidence that the standard model is incomplete at the electroweak scale. New physics at the electroweak scale, of the kind that composite Higgs models or other extensions provide, could change the nature of the electroweak phase transition. Make it first order. Provide the conditions needed to explain why we live in a matter-dominated universe. Why we exist at all. The connection between the Higgs boson's properties and the matter-antimatter asymmetry is one of the reasons physicists are so motivated to understand the Higgs at a deeper level. It's not just particle physics. It's cosmology. It's the question of why the universe has content rather than nothing. Measuring the shape of the Higgs potential directly is one of the primary goals of future collider experiments. The key measurement is what physicists call the Higgs self-coupling. In the standard model, the Higgs field interacts with itself. This self-interaction is what gives the potential its shape. The self-coupling constant controls how sharply the potential curves around its minimum. It is related directly to the Higgs mass. In the standard model, the Higgs self-coupling has a specific value. Measure it, and you can directly test whether the Higgs potential has its predicted shape. If the self-coupling differs from its standard model value, that is evidence for new physics affecting the potential. Possibly evidence for a first-order electroweak phase transition. Possibly evidence for composite structure. Possibly evidence for dark matter interactions with the Higgs field, since the Higgs is a natural portal to dark sectors. The Higgs self-coupling has not been directly measured yet. The signal requires producing two Higgs bosons simultaneously in a single collision. This process, called di-Higgs production, is extremely rare in the standard model. Its rate is roughly 1,000 times smaller than single Higgs production. With current LHC luminosity, only a handful of di-Higgs events are expected per year, buried in a much larger background. The HL-LHC expects to measure the self-coupling with about 50% precision. That is not wonderful. But it is the first direct handle on the shape of the Higgs potential. The FCC HH at 100 TeV would improve this dramatically. The rate for di-Higgs production grows strongly with collision energy. FCC HH could measure the Higgs self-coupling to a few percent, and any deviation from the standard model prediction would be enormously significant. It would tell us the Higgs potential has a different shape than expected, and a different potential shape implies new physics at the electroweak scale. Physics that might explain why we live in a universe of matter. There is one more reason the question of Higgs compositeness matters that goes beyond the hierarchy problem. The Higgs boson is the only fundamental scalar particle in the standard model. Scalar means it has spin 0. All the other particles have non-zero spin. Quarks and leptons have spin 1/2. Photons, W and Z, bosons, and gluons have spin 1. Gravitons, if they exist as quantum particles, have spin 2. But the Higgs has spin 0. This might sound like a minor technical detail. It is not. Fundamental scalar particles have special quantum properties that make them sensitive to the highest energy scales in nature. The quantum corrections that create the hierarchy problem are specific to spin-zero particles. Fermions and gauge bosons have symmetries that protect their masses. Fermions have chiral symmetry, which ensures their masses are proportional to dimensionless couplings. Gauge bosons have gauge symmetry, which forbids mass terms from appearing unless the symmetry is spontaneously broken. These symmetries restrict the kind of quantum corrections that can affect their masses. Scalar particles have no such protection in the Standard Model. Their masses receive corrections from all energy scales, pushing them toward the highest scale in the theory. This is the hierarchy problem, stated from the perspective of spin and symmetry. A composite Higgs resolves this by making the Higgs not a fundamental scalar, but a bound state. And bound states have different quantum properties than fundamental scalars. The mass of a bound state is determined by the dynamics of the binding force, not by corrections from arbitrarily high energy scales. The hierarchy problem goes away when the scalar is not fundamental. This is why many theorists consider compositeness the most natural resolution of the hierarchy problem, not because it is the most elegant, but because it is the most direct solution to the underlying issue. The hierarchy problem is about fundamental scalars being sensitive to high energies. If there is no fundamental scalar, there is no problem. At this point, the question becomes concrete. Given everything we've discussed, what happens when physicists actually run these searches at the LHC? ATLAS and CMS have searched for heavy vector resonances in dijet channels, looking for new particles decaying to pairs of quarks or gluons. They have searched in dilepton channels, looking for new particles decaying to pairs of electrons or muons. They have searched in diboson channels, looking for new particles decaying to pairs of W or Z bosons. In all of these channels, the data are consistent with the Standard Model. No significant excess has been observed above background. Mass limits on hypothetical resonances have been pushed to 2, 3, 4, and in some cases 5 TeV or beyond. This is important information. It means that if composite Higgs resonances exist, they are heavier than what we have currently probed, which means Z, the ratio of the Higgs scale to the compositeness scale, is smaller than about 10%, which means the deviations in Higgs couplings from Standard Model values are at the few percent level or below. The experimental situation is pushing composite models toward a regime where they are not completely natural in the strictest technical sense. Even composite models now require some mild degree of fine-tuning to explain why the Higgs mass is as low as it is compared to the compositeness scale. This was not the original promise of composite models, which was to be completely natural. Mildly tuned by a factor of a few percent is very different from the factor of 10 to the 34 fine-tuning in the Standard Model alone. The hierarchy problem is not solved as completely as hoped, but it is greatly ameliorated, and the models remain theoretically motivated. The search continues. The Higgs boson also connects to the question of dark matter. About 27% of the universe's total energy density is in the form of dark matter. We know it exists from its gravitational effects. It holds galaxies together. It shapes the large-scale structure of the universe. It was present in the early universe and influenced the formation of the cosmic microwave background. We have never detected a dark matter particle directly in a laboratory. We have never seen one produced in a collider. But if dark matter is a particle, it has to interact with the rest of the universe through some force. The most natural candidate for that force is the Higgs field. The Higgs couples to any particle that has mass. If dark matter has mass, the Higgs could mediate interactions between dark matter and ordinary matter. The Higgs boson could decay into dark matter particles. This would appear as an invisible Higgs decay. The Higgs is produced, and then it simply vanishes. The decay products are dark matter particles that pass through the detector without leaving a trace. ATLAS and CMS have searched for invisible Higgs decays. The current limit is that the fraction of Higgs bosons decaying invisibly must be less than about 11%. Any more than that, and we would have seen a significant reduction in the rates of other Higgs decays that we can measure. 11% is still a lot of room. A dark matter particle with the right coupling to the Higgs could easily hide within that window. If the Higgs is composite, the structure of the composite state would also affect how it couples to dark matter. The compositeness of the Higgs and the nature of dark matter might be related. If the dark matter is itself a pseudo-Nambu-Goldstone boson of the same broken symmetry that produced the Higgs, there would be natural connections between their properties. Some composite Higgs models include dark matter as a natural byproduct, not an additional ingredient grafted on, but a necessary consequence of the same structure that explains the Higgs. These are the kinds of connections that make physicists optimistic. A single framework that explains the Higgs, dark matter, and the matter-antimatter asymmetry would be extraordinary. Not all models achieve all of this, but the possibility that they could is why the theoretical work continues. The discovery of the Higgs boson was supposed to be the end of a chapter, the completion of the Standard Model. The final piece of the puzzle that began to be assembled in the 1960s and early 70s, and in one sense, it was. The Standard Model is now experimentally complete. Every particle it predicted has been found. The last to fall were the top quark, discovered at Fermilab in 1995, and then the Higgs itself in 2012. But the discovery also opened the next chapter immediately, because having the particle means you can study it, and studying it reveals that it sits in an uncomfortable place theoretically. Its mass is unnaturally small, given the quantum corrections it should receive. Its couplings match the Standard Model almost too perfectly to be consistent with large compositeness. Almost, but not quite, at the precision currently available. And the precision is going to improve by factors of 5 to 10 with the HL-LHC, and by another factor of 5 to 10 with future colliders. Each improvement is another chance for the cracks to appear, another chance for the Higgs to reveal that it is not what it seems. The community of particle physicists is united on at least one thing. The Higgs boson is not fully understood. The question of what it is made of, or equivalently, why its properties are what they are, is one of the central open questions in fundamental physics. Not a peripheral curiosity. The central question, because the answer will tell us whether there is new physics waiting to be discovered, and if there is, what kind of physics it is, and whether the machines we are planning to build will actually find it. The Higgs field is not just a technical detail of particle physics. It is what makes chemistry possible. Without the Higgs mechanism, electrons would be massless. Massless electrons travel at the speed of light. A massless electron cannot be bound to a nucleus. You cannot form a hydrogen atom from a massless electron and a proton. The electron would zip straight through, unable to be captured by the electromagnetic attraction. Chemistry requires atoms. Atoms require electrons with mass. Electrons have mass because they interact with the Higgs field. So the Higgs field is the prerequisite for chemistry. And chemistry is the prerequisite for life as we know it. The specific value of the Higgs vacuum expectation value, 246 GeV, matters enormously. A different value would produce a different electron mass. A different proton to electron mass ratio. Different chemistry. Different bond strengths. Different properties of water, carbon, oxygen. The specific value of the Higgs vacuum expectation value is not something the standard model predicts. It is a free parameter, a number put in by hand. We measure it and write it down. And the fact that the number we measure happens to be the one that allows for complex chemistry is not something the standard model explains. It just is. Any deeper understanding of the Higgs field is an attempt to explain why it is. Why the vacuum expectation value is 246 GeV. Why the Higgs potential has the shape it has. Why electroweak symmetry breaking happened at the energy scale it did. The question of what the Higgs boson is made of is not abstract. It is a question about why the universe has the structure it has. Why mass has the values it has. Why atoms form. Why chemistry works. Why we exist. There is something almost poetic about the situation. The field that gives everything its mass is the field we understand least. The particle that was supposed to complete the picture turned out to complicate it. The Higgs boson was found exactly where the theory said it should be, with exactly the properties the theory said it should have. And somehow, that is the most unsettling outcome of all. Because a theory that works that well, that matches reality that precisely, and still contains such a flagrant theoretical problem as the hierarchy problem, is telling you something. It is telling you that it is not the final word. That something lies beneath. That there is a layer of reality we have not yet reached. Physicists in the 1930s were in a similar position. They had a beautiful framework for electrons and photons. It worked extraordinarily well. And yet they knew it was incomplete, because the nucleus sat there unexplained, with forces that the electron-photon framework could not account for. The resolution was the strong and weak nuclear forces. Entirely new kinds of interaction. New particles. A whole new realm of physics that the tools of the 1930s were simply not powerful enough to see. The Higgs boson may be telling us something similar. That beyond what we can currently see, beyond what our machines can currently probe, there is a new realm. New forces, new constituents, new structure. And the question is not whether something is there. The theoretical arguments are compelling enough that most physicists believe something new must exist at some scale. The question is whether we will build the machines capable of looking at the right energy. You could spend a lifetime studying the Higgs boson and still not reach the bottom of it. Physicists have. And many of them will say that the more precisely they measure it, the more interesting it becomes. Because every measurement is a clue. Every deviation from prediction, however small, is a potential window into new physics. Every measurement that agrees with the standard model narrows the space of alternatives. Slowly, measurement by measurement, collider run by collider run, the picture sharpens. We are learning what the Higgs is not, eliminating the alternatives. And eventually, that process of elimination leads to an answer. That is how physics works. That is how we found quarks. That is how we found the W and Z bosons. That is how we found the Higgs itself. Decades of precision, followed by the moment when the answer becomes undeniable. We are somewhere in the middle of that process. For the Higgs, maybe not halfway, maybe closer to the beginning. The answer might take the rest of this century. It might take longer. But the question is alive. It is being worked on by thousands of people across dozens of countries. And when the answer comes, it will reshape physics in ways that are genuinely hard to predict. Because the history of the Higgs is a history of surprise. Nobody expected the hierarchy problem to be as severe as it is. Nobody expected the Higgs to look as standard model-like as it does after all this time. Nobody expected the particle we had been searching for since the 1960s to raise so many new questions upon its discovery. The universe has a way of being more complicated than expected, and also, somehow, more elegant. These two things coexist in the Higgs boson, an object that is simultaneously the simplest possible implementation of a mechanism we know must exist, and the most theoretically uncomfortable particle in the standard model. A particle that might be fundamental, or might dissolve at higher energies into something smaller and stranger. A particle that we found, that we study, that we measure, that we still do not fully understand. There is a concept in particle physics called the Higgs portal, and it is one of the most important ideas connecting the Higgs boson to some of the biggest unsolved problems in physics. A portal, in this context, is a term physicists use for an interaction that links the standard model to some hidden sector of particles that doesn't interact with ordinary matter through electromagnetism or the strong force. The Higgs portal works like this. The Higgs field couples to any particle that has mass. If there are new particles beyond the standard model, and if those particles have mass, then by the logic of the Higgs mechanism, they should interact with the Higgs field. The Higgs field is, in a very literal sense, the one ingredient that connects to everything with mass. This makes the Higgs a uniquely powerful probe of new physics. Not just a thing to study. A tool. A window. If dark matter particles are massive, they should interact with the Higgs. And that interaction would leave a mark on both the Higgs boson's properties and on direct dark matter searches. If there are new heavy particles connected to the hierarchy problem, whether they are superpartners, technicolor resonances, or Kaluza-Klein modes, they interact with the Higgs. And those interactions modify the Higgs couplings in measurable ways. If there are additional Higgs-like particles, perhaps because the Higgs sector is more complicated than the minimal one in the standard model, they mix with the observed Higgs boson and alter its properties. Every one of these scenarios leaves a fingerprint in the precision measurement of the Higgs boson. Every coupling deviation, every branching ratio anomaly, every invisible decay fraction carries information about what lies beyond. This is why physicists sometimes describe Higgs coupling measurements as model-independent probes of new physics. You don't have to commit to a specific theory. You just measure everything you can. And if anything deviates from the standard model prediction, you know something is there. Something is interacting with the Higgs. And then you work backward to figure out what. There is also the question of whether there is only one Higgs boson. The standard model requires exactly one Higgs doublet. 4 components, 1 physical particle. But there is no deep symmetry principle in the Standard Model that forbids additional Higgs doublets or additional scalar fields more broadly. Many extensions of the Standard Model include a richer Higgs sector. The 2 Higgs doublet model, or 2HDM, is one of the simplest. It postulates 2 complex doublets of scalar fields instead of 1. That gives 8 real components. 3 of them get absorbed by the W and Z bosons, as in the Standard Model. The remaining 5 become physical particles. 2 of them are neutral scalars, usually called H and H, where H is the lighter one and is identified with the Higgs boson we observed. 1 is a neutral pseudoscalar, usually called A, and 2 are charged scalars, usually called H+ and H-. The existence of charged Higgs bosons would be a smoking gun signature of an extended Higgs sector. The Standard Model Higgs has no electric charge. A charged scalar particle is something completely new. Both ATLAS and CMS have searched for charged Higgs bosons. They haven't found them. Mass limits of several hundred GeV to a few TeV have been placed, depending on the assumed couplings. But there is a large allowed parameter space where charged Higgs bosons could exist and still evade current searches. Supersymmetry requires a 2 Higgs doublet model. The Minimal Supersymmetric Standard Model, or MSSM, which is the simplest supersymmetric extension of the Standard Model, necessarily has 2 Higgs doublets. This is because supersymmetry requires the Higgs sector to be extended in a specific way to avoid mathematical inconsistencies. The ratio of the vacuum expectation values of the 2 doublets, called tan beta, is one of the key parameters of the MSSM, and searches for the additional Higgs bosons of the MSSM have been extensive. So far, the additional particles have not been found, but the search continues. And for composite Higgs models, the situation is different. The composite Higgs often comes with a spectrum of additional scalar particles, some of which are heavier neutral scalars from the same composite structure. The lightest of them, the one we observe, has the properties of a pseudo-Nambu-Goldstone boson. The heavier ones, if they exist, would appear at the compositeness scale. Finding them would confirm the composite nature of the Higgs directly. The electroweak symmetry itself is worth understanding in more detail. Because it is a beautiful structure, and understanding it makes the Higgs more vivid. At energies much higher than the mass of the W and Z bosons, the electromagnetic force and the weak nuclear force are not separate. They are 2 aspects of a single electroweak force. The electroweak force is described by a symmetry group. The specific group is SU2 cross U1 in the language of mathematics. SU2 is the group of 2 by 2 unitary matrices with determinant 1. U1 is the group of unit magnitude complex numbers. In this symmetry group, there are 4 gauge bosons. The 3 W bosons, called W to the plus, W to the minus, and W0, and 1B boson. These 4 particles are the carriers of the electroweak force in its unbroken state. They are all massless. Above the energy of electroweak symmetry breaking, the universe would look like this. 4 massless gauge bosons, massless quarks and leptons, no electromagnetic force and weak nuclear force as separate entities, 1 unified electroweak force. When the Higgs field settles into its minimum and electroweak symmetry breaks, these four-gauge bosons mix. The W0 and B boson mix together. One combination becomes the Z boson. Another combination becomes the photon. The W to the plus and W to the minus don't mix with anything. They become the charged W bosons. Three of these four-gauge bosons acquire mass through the Higgs mechanism. The W to the plus, W to the minus, and Z boson. Their masses are about 80 GeV, 80 GeV, and 91 GeV, respectively. One of the four remains massless, the photon. Because there is a residual symmetry after electroweak symmetry breaking, the U1 of electromagnetism, that protects the photon from acquiring mass. This is the entire origin of electromagnetism as we know it. The electromagnetic force is the shadow of the unbroken electroweak symmetry. The photon is massless because a remnant symmetry survived the Higgs mechanism. Electrons are charged because they interact with that remnant U1. The structure is extraordinarily elegant. And all of it hinges on the Higgs field and its symmetry-breaking vacuum expectation value. If the Higgs field didn't break the electroweak symmetry, there would be no distinction between the electromagnetic force and the weak nuclear force. No massless photon. No long-range electromagnetic interactions. No atoms. The Higgs field is what gives the universe the force structure we observe. The weak nuclear force is responsible for radioactive beta decay. This is the process where a neutron decays into a proton, an electron, and an antineutrino. It is responsible for the solar fusion reactions that power the sun. Without the weak force mediating certain nuclear reactions, the sun would not shine. The weak force operates through the exchange of W and Z bosons. Because these bosons are massive, about 80 to 90 GeV, the weak force has a very short range. The range of a force is inversely proportional to the mass of the carrier particle. Electromagnetism has infinite range because the photon is massless. The weak force has a range of about 10 to the power of -18 meters, much smaller than the size of a proton, because the W and Z bosons are heavy. The Higgs gives the W and Z their mass. So the Higgs is ultimately responsible for the short range of the weak force, and therefore for the specific character of nuclear physics as we observe it. The rates of nuclear reactions in stars, the lifetimes of radioactive isotopes, the way nuclear fusion proceeds inside the sun. All of this traces back through the masses of the W and Z bosons to the Higgs field. If the Higgs vacuum expectation value were different, the W and Z masses would be different. The range of the weak force would be different. The rates of stellar fusion would be different. Stars might shine for different lengths of time, or not at all. The specific value of the Higgs vacuum expectation value, 246 GeV, is not arbitrary. It is the value that produces the universe we observe, and we do not know why it has that value. That is the deepest version of the question. There is a school of thought in theoretical physics that says we should not be bothered by the hierarchy problem, that it is not actually a problem. That fine-tuning, even to 1 part in 10 to the 34, is not physically wrong. It is just aesthetically unpleasant. This position is sometimes called naturalness, skepticism, and its proponents have grown more vocal since the LHC failed to find the supersymmetric particles or composite resonances that naturalness arguments predicted should be there. The argument goes something like this. We observe a universe with the specific values of physical constants it has. We should not expect those values to be explained by a theoretical preference for natural numbers. Nature does not care about our aesthetic sensibilities. Fine-tuning is only a problem if you assume some prior probability distribution over the possible values of physical constants. And there is no physically motivated reason to choose any particular distribution. The anthropic principle adds another dimension. If the universe had a vastly different Higgs mass, complex chemistry might not exist. We might not exist. So, of course, we observe a universe where the Higgs mass allows for complex structures. We could not observe anything else. The fine-tuning might be a selection effect. We observe the values we observe because only those values allow for observers. This argument has some validity. And it makes some physicists less worried about the hierarchy problem than they used to be. But most theoretical physicists still find the hierarchy problem deeply unsatisfying. Because the naturalness skepticism position, taken to its logical extreme, would mean we should not expect any theory to explain the values of physical constants. We should just accept them as they are. And that would mean the end of the search for deeper understanding. It would mean the standard model is the final theory, not because we have proven it is, but because we have decided to stop asking why. Most physicists are not willing to go there. The question, what is the Higgs made of, is, in part, a refusal to accept that the hierarchy problem is meaningless. It is an insistence that there is something to understand, and that we can find it. The searches for new physics at the LHC have produced something interesting, even in the absence of a discovery. They have produced extremely detailed maps of where new physics is not. Every mass limit placed on a hypothetical particle is a constraint on theory. Every channel searched, without finding an excess, is information. When you combine all of the constraints from all of the LHC analyses, you get an extraordinarily detailed picture of the allowed parameter space for models beyond the standard model. Most of the simple, natural, minimal versions of those models are now excluded. The minimal supersymmetric standard model with natural parameters is essentially ruled out. The simplest composite Higgs models with resonances at 1 or 2 TeV are constrained. What remains are the more complex versions. More parameters, more ingredients, less predictive, less elegant. This is the uncomfortable reality of the current situation in particle physics. The simple answers didn't show up. What's left are the complicated ones. And complicated models are harder to test, harder to falsify, and harder to be confident about. This is not a crisis in the sense of the theory being wrong. The standard model continues to be correct. It is a crisis in the sense that the physics beyond the standard model is proving more elusive than expected. And that forces physicists to confront difficult questions about what they should be looking for next. Some have responded by developing more creative theoretical ideas. The relaxation, proposed by Peter Graham, David Kaplan, and Surjit Rajendran in 2015, is one example. The relaxation is a new scalar field that starts with a large Higgs mass and dynamically relaxes it to its observed small value as the universe expands and cools. It is a cosmological solution to the hierarchy problem, not asymmetry, not compositeness, but dynamics in the early universe. It makes very different experimental predictions. And it represents the kind of lateral thinking that the field is generating in the absence of the expected discoveries. The actual process of measuring the Higgs boson is more intricate than most people realize. The Higgs boson is produced in the collisions at the LHC, but it doesn't live long enough to travel any macroscopic distance. Its lifetime is about 1.6 times 10 to the power of negative 22 seconds. That is fantastically short. In that time, traveling at close to the speed of light, the Higgs moves less than 1/10,000th of a millimeter before it decays. So you never see the Higgs boson directly. You see the particles it decays into, and then you work backward to figure out that a Higgs boson was there. The Higgs has several major decay modes. The most common, about 58% of the time, is decay into a pair of bottom quarks. The bottom quark and its antiparticle are produced together. But bottom quarks are difficult to detect cleanly because the LHC produces enormous numbers of quark pairs through other processes. The bottom quark decay channel was only observed with high significance in 2018, 6 years after the initial discovery. The second most common decay, about 22% of the time, is into a pair of W bosons. But one of the W bosons is off-shell, meaning it doesn't have enough energy to be a real W boson. This makes the reconstruction complicated. About 2.6% of the time, the Higgs decays into a pair of Z bosons. This is the golden channel, because both Z bosons can decay into pairs of leptons, electrons, or muons. These are clean signals in the detector, easy to identify. The original discovery was largely based on the decay into 2 Z bosons decaying into 4 leptons, and the decay into 2 photons, which happens only about 0.2% of the time. Very rare. But photons are exquisitely well measured in the detector. The 2-photon decay channel was one of the 2 key channels for the initial discovery. Each of these decay modes is sensitive to different aspects of the Higgs couplings. The decay to bottom quarks measures the coupling to bottom quarks. The decay to W bosons measures the coupling to W bosons. The decay to 2 photons involves loops of top quarks and W bosons, so it is sensitive to the coupling to top quarks as well. By measuring all of these rates and comparing them to standard model predictions, you get the complete picture of the Higgs couplings. And any deviation in any channel is a potential signal of new physics. This is why Higgs coupling measurements are so central to the search for physics beyond the standard model. They are not just interesting for their own sake. They are probes of everything that could be interacting with the Higgs, including whatever the Higgs might be made of. There is one more aspect of the Higgs boson that deserves attention. The question of whether it is stable, not in the sense of how long it lives before decaying. We know that. About 10 to the power of negative 22 seconds. But in the sense of whether the Higgs field itself, the background field that permeates all of space, is in a stable state or a metastable one. This is a question about the vacuum of the universe. The vacuum is not empty. It is a state of the Higgs field, sitting at its minimum value of 246 GeV. But the shape of the Higgs potential at very high field values depends on quantum corrections from the top quark and other particles. And those corrections, calculated within the standard model using the measured value of the top quark mass and the Higgs mass, suggest something disturbing. At very high field values, far larger than 246 GeV, the Higgs potential may develop another, deeper minimum. If that deeper minimum exists, then the vacuum we live in is not the true vacuum. It is a false vacuum, a metastable state that could, in principle, decay to the true vacuum. This decay would proceed by quantum tunneling. A bubble of true vacuum would nucleate somewhere in space and expand at the speed of light. Inside the bubble, the laws of physics would be different. The Higgs vacuum expectation value would have a different value. Particles would have different masses. Chemistry, as we know it, would not work. This process, if it happened, would be completely invisible until the bubble wall arrived at your location. And it would arrive at the speed of light, so there would be no warning. Now, the good news is that calculations suggest the vacuum is either stable or extremely long-lived. The lifetime of a metastable vacuum is estimated to be vastly longer than the current age of the universe. So there is no practical concern. But the question of whether we live in a stable or metastable vacuum is a deep one, and the answer depends sensitively on the exact values of the top quark mass and the Higgs mass. The current measurements of both sit very close to the boundary between stability and metastability. It is not clear which side we are on. Some calculations say stable. Some say metastable. The uncertainties in the top quark mass are large enough that we can't be certain. Better measurements of both the top quark mass and the Higgs mass are needed. And, more importantly, a deeper understanding of the Higgs potential at high field values, which requires knowing what the Higgs is made of. Because if the Higgs is composite, its potential at high field values is completely different from the elementary Higgs potential. The question of vacuum stability is yet another reason why understanding the structure of the Higgs field matters. Not just for particle physics, but for the ultimate fate of the universe. The searches at ATLAS and CMS continue. Analyses of run. 3 data from the LHC are ongoing. Teams of hundreds of physicists pore over the data, looking for deviations, excesses, anomalies. Anything that does not fit the standard model. Anything that might be a signal of what lies beneath. And when they finish with run 3, there will be the high luminosity upgrade. And after that, the debate about future colliders. Every one of those future machines is, at its core, a machine for asking the same question. What is the Higgs boson made of? The answer, when it comes, will tell us whether there are new forces in nature, new constituents of matter, new dimensions of space, or some mechanism for naturalness that no one has thought of yet. It will be one of the great discoveries in the history of science. Or it will be the absence of a discovery, which would force an even deeper rethinking of what we understand about the universe. Either outcome changes everything. And either outcome will be the result of experiment, of data, of measurements made by machines built over decades, by thousands of physicists in dozens of countries, working on one of the oldest questions in human inquiry. What is matter made of? At the deepest level we can reach. The Higgs boson is the current frontier of that question, and we are standing at it right now. Before we talk about where this search is ultimately heading, it helps to understand how particle physics actually works as a scientific enterprise, because it is different from almost every other field of science. A particle physics experiment at the LHC is not designed, run, and analyzed by a single team. The ATLAS detector is operated by a collaboration of thousands of physicists from more than 180 institutions in around 38 countries. The CMS detector has a similar collaboration. These are not small research groups. They are distributed international organizations with a complexity comparable to a small country's scientific infrastructure. When Atlas publishes a result, it carries the names of thousands of authors. Every significant analysis goes through multiple rounds of internal review before it reaches the public. This might sound bureaucratic. It is. But it is also a quality control system of extraordinary rigor. A result that has survived internal scrutiny by 5,000 physicists is a result that has been stress-tested in ways that smaller experiments cannot match. The flip side is that particle physics operates on long timescales. The LHC took decades to design and build. The Atlas and CMS detectors were themselves massive engineering projects spanning 15 years of construction. When physicists talk about the HL-LHC upgrade, they are talking about an upgrade that will take most of the 1920s to install and commission. When they talk about the FCC, they are talking about a machine that would begin operations perhaps in the 1950s. These are timescales that exceed individual careers. Most of the physicists currently working on the conceptual design of the FCC will not be alive when it produces its first results. This is a long game. And it requires a kind of institutional commitment that is rare in human endeavors. The question of what the Higgs boson is made of might not be answered in the professional lifetime of any person currently working on it. It might be answered in the lifetimes of graduate students who are just starting their careers today. Or it might be answered by their students. The search has its own timescale, determined not by what physicists want, but by what nature requires. There is a deeper philosophical point embedded in everything we have discussed. When physicists ask, "What is the Higgs boson made of?" they are asking whether there is a more fundamental level of description of reality than the one we currently have. Every time we have asked this question in the history of physics, the answer has been yes. Atoms are made of nuclei and electrons. Nuclei are made of protons and neutrons. Protons and neutrons are made of quarks. Each step revealed a new layer of structure, a new force governing that structure, a new set of constituents. Each step required new machines and new theoretical frameworks. Each step changed our understanding of what matter is. There is no known reason why the quarks and leptons of the Standard Model should be the final layer. There is no theorem that says the descent into structure must stop here. The theoretical arguments, particularly the hierarchy problem, actively suggest it doesn't stop here. And the historical pattern says it probably doesn't stop here. But we don't know. We genuinely don't know whether there is structure below the quarks. We don't know whether there is structure inside the Higgs. We are asking the question, and we are waiting for nature to answer. That is the honest position, and it is a position worth sitting with, because it means we are at a frontier, a real frontier, not a metaphorical one, the edge of what is known. And the question on the other side of that edge, the question of what the Higgs boson is actually made of, might be one of the most fundamental questions a human mind has ever asked. It is asking what reality is made of at its smallest scale. And we don't know the answer yet. But we have the tools and the will to find out. The story of how the Higgs boson was predicted is itself remarkable. In 1964, 3 groups of physicists, working independently, published papers describing essentially the same mechanism. Robert Brout and François Englert in Brussels. Peter Higgs in Edinburgh. Gerald Guralnick, Carl Hagen, and Tom Kibble in London. All three papers appeared within a few months of each other. All three described how a scalar field could break gauge symmetry and give mass to gauge bosons. The mechanism is now called the Brout-Englert-Higgs mechanism in some contexts, and the Higgs mechanism in others. The particle it predicts is called the Higgs boson, after Peter Higgs, who specifically emphasized in his paper that there should be a massive scalar particle associated with the symmetry breaking. The other authors focused more on the mechanism itself. Higgs focused on the physical particle the mechanism implied. The Nobel Prize in Physics in 2013 was awarded to Peter Higgs and François Englert, who by that time was the sole surviving member of the Brout-Englert collaboration. Robert Brout, having passed away in 2011, Gerald Guralnick, Carl Hagen, and Tom Kibble were not included, a decision that remains controversial in the physics community. The Nobel Prize is limited to 3 recipients, and 6 people independently contributed to the discovery of the mechanism. What makes the story remarkable is that none of these physicists expected to wait 48 years for experimental confirmation. When the papers were published in 1964, the electroweak theory itself did not yet exist in its modern form. Steven Weinberg and Abdus Salam independently developed the electroweak theory in 1967 and 1968, incorporating the Brout-Englert-Higgs mechanism as its central component. Gerard Hooft and Martinus Veltman proved in 1971 that the electroweak theory was mathematically consistent, that it was what physicists call renormalizable. Without renormalizability, the theory would give infinite answers to physical questions and would be useless for calculation. With it, the theory became predictive in an extraordinary way. The discovery of the W and Z bosons at CERN in 1983 was the first major triumph of the electroweak theory. The masses predicted, about 80 and 91 GeV, were confirmed with remarkable precision. At that point, the existence of the Higgs boson was not in serious doubt. The only question was its mass, and the search for it took another 30 years. That search required building the Large Electron-Positron Collider at CERN in the 1980s, which searched up to a Higgs mass of about 114 GeV without finding it. Then the Tevatron at Fermilab, which searched higher still without a definitive discovery. Then the LHC, which was specifically designed to guarantee discovery of the Higgs regardless of its mass. The logic was simple. The LHC runs at energies high enough to produce Higgs bosons in any mass range up to about 1 TeV. If the Higgs exists and has a mass in that range, the LHC would find it. Either you find the Higgs, or you find something else that is doing the job of the Higgs, because something must be. Electroweak symmetry must be broken. The W and Z bosons are massive. Whatever is causing that must show up. The LHC was designed as a machine for answering this question once and for all. And it did, in 2012, with a mass of 125.25 GeV. Sitting at the bottom of the allowed mass range, lighter than most theorists had expected. And lighter in a way that would prove to be significant. Because a lighter Higgs means a longer-lived vacuum. But a lighter Higgs also means a smaller hierarchy problem in absolute terms, even as it persists in relative terms. and a lighter Higgs means that the couplings to certain particles, like the bottom quark and the tau lepton, are smaller and harder to measure, making the precision program more demanding. The universe chose the specific Higgs mass that is hardest to study in certain ways, and that sits precisely at the stability edge of the vacuum. It is almost provocative. There is one final aspect of the Higgs question that connects to the very beginning of physics, the ancient question of what matter is made of. The Greek philosophers proposed atoms, indivisible units of matter from which everything is built. Modern physics replaced those atoms with electrons, protons, and neutrons, and then replaced those with quarks and leptons and force carriers. And now we have the Standard Model, with its 16 fundamental particles and the Higgs. Each time we thought we had reached the bottom, we found another layer. The word atom itself, from the Greek for uncuttable, turned out to be misnamed. Atoms are divisible into nucleus and electrons. The nucleus is divisible into protons and neutrons. The proton is divisible into quarks. Are quarks divisible? Is the electron divisible? Is the Higgs boson divisible? We don't know. The current experimental evidence says that if there is internal structure, it is at a scale below what our best instruments can resolve. Quarks and electrons look point-like to the precision of current experiments. But so did atoms before the experiments that revealed nuclear structure. So did protons before the experiments that revealed quark structure. The pattern is consistent and sobering. Every generation believed it had reached the bottom. Every generation was wrong. The question is not whether the pattern will repeat. The pattern has repeated too many times to dismiss. The question is, when? And with what machines? And with what theoretical insight to interpret what the machines find? The Higgs boson stands at the center of the current generation's attempt to go deeper. It is the place where the Standard Model is most vulnerable, where theory is most clearly incomplete, where the gap between what we know and what we need to know is widest. And that makes it the most interesting place in all of physics. The most interesting particle we have ever found. Not the most exotic, not the most energetic, but the most theoretically fraught. The one that carries the most unanswered questions. The one that, when finally understood, will tell us the most. And that is what makes it unlike any particle physicists have ever studied before. Every other fundamental particle either slots cleanly into a known category or behaves as theory predicted. The Higgs does neither. It sits at the intersection of everything we understand and everything we don't. The Higgs boson is not finished with us. We found it. We confirmed it exists. We measured its basic properties. And then it handed us back a list of questions longer than the one we started with. That is what a truly significant discovery does. It does not close chapters. It opens them. The hierarchy problem, the question of naturalness, the nature of electroweak symmetry breaking, the matter-antimatter asymmetry, the origin of dark matter, the stability of the vacuum. All of these connect to the Higgs. All of these are unanswered. And the question of what the Higgs is made of sits at the intersection of all of them. Understanding the structure of the Higgs, or confirming that it has no structure, will not answer all of these questions. But it will constrain the answers dramatically. It will tell us which theoretical frameworks are right and which are wrong, which machines to build next, which ideas to pursue. The answer to one question becoming the compass for the next generation of questions. That is how science advances. Not in straight lines, in spirals. Each revolution bringing you closer to something that keeps receding as you approach it. And yet, you approach it. Each measurement more precise than the last. Each machine more powerful than the one before. Each generation of physicists inheriting a richer set of tools and a narrower set of mysteries. The Higgs boson is the current center of that spiral. And we are turning. Whatever the Higgs boson turns out to be, the act of asking what it is made of is itself significant. It is a refusal to accept the catalog. A refusal to write in the free parameters without asking why. A refusal to call something fundamental without checking. That refusal is the engine of physics. It is what drove the experiments at Stanford. It is what drove the construction of the LHC. It is what drives the planning of everything that comes next. The question is alive. The machines are running. And the universe, as it always has, will answer in its own time, in its own way, with exactly the kind of surprise that makes every answer worth waiting for. Good night.